In this video, we'll discuss exponential growth and decay, basically some application of calculus in some biological or physics problems, in physics, or even financial problems. So there are lots of in many situations. So you are given a quantity function, right? Either value or population function. So the rate of change of this quantity basically is proportional to its size. So that's what's going on here. So this is a phenomenon we want to model using exponential functions, right? So let's start from a general setup. We have y of t, and t is time. Y of t here is the value of a quantity. You can imagine. So that's the uh, the money value in your bank account or populations in some area or some radioactive material, right? Substance at time t. So a good property of this thing here is the rate of change, the rate of change of y. So the y here with respect to t time, right? By our discussion so far, so this is basically dy over dt, the rate of change, right? And is proportional, right? Proportional uh, to what? To its size, right? To the original function. To its size, let's call that y of t, right? At any time t, right? And and by this property of this material or something, right? Y, we can set up equation for this function, which means dy over dt is proportional to y of t, right? So basically the ratio here is a constant. We call the constant to be k. And for some constant k, right? K here the constant. So you can see that if you have k here is positive, right? Which means the rate of change is positive. So this is basically the law of natural growth. What happens here is, for example, populations of some bacteria or something, right? Also, this also related to economics. If you try to compound the interest rate continuously, right? That's also what is going on. So this is continuously compounded interest. So that's another thing in which this satisfy this equation where the constant is positive. Your money is getting more and more, population is getting bigger and bigger, right? Greater and greater. And if you have k here is less than 0, right? The rate of change is less than zero because the value normally is positive. So y normally is positive. So if you have k less than zero, the rate of change less than zero. So this is called the law of natural decay, right? So a good application for this equation will be the radioactive uh, decay, right? And now our natural question here is which function satisfy this equation here, right? Which function whose derivative is itself, right, and time constant. By our discussion of the derivative elementary functions, we know that one function satisfies this equation, which is the exponential function, right? K here should be the constant of time t in the exponent position, right? So by our under discussion of derivative so far, so y of t should equal to e to kt, right? So the derivative of this function is k times e to kt, which is good. But by the constant multiple rule, this function, if you multiply by constant, this is still good, right? So in this case, if you have your function is a constant, which is k times e to kt, then what happens here is dy over dt is c times e to kt times k, which is k times y of t, right? This function satisfies the equation we obtain from the either from physics or biology or economics, right? So what is the y zero? You wonder what is y zero? We know that y of zero is what is c times e to zero, and e to zero is one, so this is c, right? So this is the initial population or initial mass of the radioactive material or initial money in your bank account, right? And then y of t should be y of zero times e to kt, right? So this is basically how do we set up this equation for this natural growth or natural decay. So let's see a example. Example here. So this equation here only applies if you have uh, this condition here are satisfied. The rate of change of the quantity is proportional to this the size of this quantity, right? The size of y of t. So we have a bacteria culture here, right? A bacteria culture containing we put in 100 cells, containing 100 cells, right? And grows at a rate, right? Normally you have enough food, you have enough uh, space, right? Proportional. So this is our K assumption, proportional, proportional to it, to its size, right? If you have, okay, so now what do we want to know? So we want to know, okay, so this is given another condition after 1 hour right? And the population or population of the cells, right? Increases to 420 cells, right? So what do we want to do? What do we want to know? We want to know two things. First, we want to find uh, expression uh, of the population of bacteria after uh, T hours. So that's what we want to do first, find a population bacteria, right? So based on the assumption, the rate of change is proportional to its size. So your function look like this, right? So let's use population function. Let's use capital P, right? Let P of T be the population uh, of the bacteria at time t, right? So we know that P of t should equal to P of 0 times e to kt, right? There are two unknowns. One is P0, but P0 is given in this case, right? Notice, you know that P of 0 is 100. You also know that P1 here is 420, right? After 1 hour, the number of cells increased to 420, right? So, so plug in the first condition, you get what? You get P of t equal to 100 e to kt. Plug in the second condition, we get 420 is 100 e to k times 1, right? Solving for k, you get 420 over 100 is e to k. So k here is natural log of 4.2, right? So our population function P of t equal to 100 e to the power natural log of 4.2 times t, right? So that's what we get for the population function. Let's write down the second question here. And after how many hours? How many hours the population reach let's say 10,000, right? So that's a question here. All you want to do is set up equation, which is 100 times e to natural log of 4.2 times t equal to 10,000, right? Then you solve for t, right? Divide by 100 and also take a natural log. And you divide by the natural log of 4.2, right? So t here should equal to natural log of 100 over natural log of 4.2, right? You can round it to the next integer. So we get approximately how many hours if we want to get 10,000 cells of this material.